Now that we've visualized the coordination interactions, let's go ahead and take a look at the source code. So this will be, of course, the implementation of the simple blocking bounded queue. We have some state method. We have some state, which are the mlist and capacity fields. And of course, this internal state has to be protected against race conditions. The constructor does not have to be protected against race conditions. Why? Because the constructor is only called once, and it's only called in a single thread. If a constructor is called multiple times in multiple threads, then something very seriously has gone wrong with Java, so that's not going to happen. The thread can wait using the condition, the sort of implicit condition variable that's part of every Java built-in monitor object. So this is the guarded suspension pattern. When the take method is called, that will block to acquire the intrinsic lock. And then while the queue is empty, which it would be if it starts out with nothing in it, we have to wait, which, as you recall, releases the lock and puts the thread to sleep. A good rule of thumb to be violated only if you really know what you're doing is to check the condition and wait in a loop. So you almost always want to do that. There's a few exceptions. You may actually run across them in one of the upcoming assignments, but generally that's what you want to do. And the reason for this, the reason for doing it in a loop, is because you don't know whether the resource is available just because you were notified that it might have been available, because someone else may have come along and stolen it in the meantime between when you were notified and when you got the lock and got a chance to check. And this is really actually in the context of Java built-in monitor objects, the fact that you only have a single wait queue means you're going to be awakened an awful lot of times. You're going to be awakened when someone puts stuff in the queue. Everybody's going to wake up. You're going to be awakened when someone takes something out of the queue. Everybody's going to be waked up. And most of the time, it's not about something you actually care about. So using the loops is really, really important for built-in monitor objects in many cases. And as we said before, the non-determinants of concurrency might mean that between the point when you were awakened and when you loop back around with the lock held, someone else may have come along and grabbed the resource in the meantime. Something else you have to be wary of is something called spurious wake-ups. And you can read about spurious wake-ups here. This has more to do with the way in which people implement the underlying primitives in the hardware to wake things up and notify them in multi-core and multi-processor systems. It's a very obscure sort of edge case that probably happens once in a blue moon. But since you've already got to put loops anyway, for the most part, you might as well just suck it up and deal with it. So a thread that's blocked on wait won't continue until it's notified that the condition expression it's waiting for may be true. And as this illustrates, here we were blocked in take on wait. When you're putting something, it adds something to the list. So now there's a possibility that you could be able to get something if you're awakened. And as you can see here, this guy is going to check to see whether or not it's full. And so this particular check is going to check to see if we're full. This actually should be while is full, not mlist is full. And then notify is called by put to wake everybody up. Again, that's because we have this crazy single wait queue problem with built-in monitor objects. When a waiting thread is notified, several things happen. So you wake up and you obtain the lock. You reevaluate the condition expression. And then you only continue after you have been able to satisfy that condition, and then you have to notify everybody. By the way, there's no problem calling poll after notify. It may look like it's backwards somehow, but even though you've woken everybody up at this point, or you've begun the process of waking them up, they can't actually make any progress until we leave the critical section here and the lock is automatically released. OK, so we release the lock when we're done, and that's basically the implementation. Now, the thing that's interesting about this is it looks complicated at first glance, but when you get the hang of programming with these mechanisms, it's very canonical. You always do things in more or less the same way. And it's very much the same way that you do it with the condition objects. It's just that those let you separate the weight sets in a finer grained manner.